Here's a brief guide to help you get started with setting up your own XSpeech model. So there's a number of different ways that you can try and set up an XSpeech model. As you get more and more advanced, you might use your own scripts for pre and post processing data. There's also a MATLAB toolbox that we provide via the OpenEarth repository. There's lots of scripts to help you set up and run XSpeech models and to analyze your data. And finally, there's also a set of tools within the Delft dashboard MATLAB program that is also freely available on the OpenEarth repository that you can use to set up your XSpeech model. Anyway, however you set up an XSpeech model, you will have a simulation folder that should contain at least an XSpeech executable or a link to the XSpeech executable, a file called params.txt, which is where all the model parameters are defined, a depth file, a grid file, and some input files such as wave input files, water level input files, and any other files for extended functionality, so things such as HUD layers, groundwater flow, etc. They all have their own input definition files. Starting with the grid file, there's a couple of different grid types that you could have. You could have a one-dimensional grid, typically used for cross-shore profile models, shown in the left figure. You could have a two-dimensional but rectilinear grid, so that would be a 2DH XSpeech model. So it's rectilinear but not uniform necessarily in grid size in the longshore and in the cross-shore direction. And you can have a two-dimensional curvilinear grid, shown in the right column. And typically for that you need some more advanced tools such as the Delft 3D RGF grid tools to develop your grid for an XSpeech model. When setting up your computational grid, you should consider that XSpeech assumes that you're using a local coordinate system, which is defined in meters, and the local coordinate system has a first dimension, an X dimension pointing east, and a second dimension, a Y dimension pointing north. Most local coordinate systems such as UTM follow this convention. You can set your grid up within this local coordinate system by specifying where the origin of your offshore boundary is, X ORI and Y ORI, and you can also give it a rotation relative to the local coordinate system, or rotate the entire coordinate system relative to east. You also have to set up a directional grid for your wave bins, so for your shortwave energy balance, which are defined between theta min and theta max with a directional spacing of d theta. You have options within XSpeech to define the wave directions either in the nautical convention, so as defined as 0 degrees would be waves coming from the north, and 270 degrees would be waves coming from the west, or in a Cartesian system where 0 degrees would be waves propagating in the x direction, and 90 degrees would be waves propagating towards the y direction, towards the north. When setting up a grid, you also, of course, need to think about the grid resolution, so the grid sizes. Typically, the resolution should be sufficient to describe the features, the hydrodynamic and morphodynamic features of interest. So, say 5 to 10 grid cells per morphodynamic feature, and also think about the kinds of morphodynamics you're expecting. So, for instance, dune erosion would be also have dune steepening, so you want to be able to produce the scarping of the dune correctly. You also need at least 10 to 20 grid cells per wavelength that you're modeling. So the short wavelength will typically be in the order of 10 meters. In the standard XSpeech surfbeat model, you're not actually resolving the short waves, but you are resolving the long waves, the infragravity waves, which have a length scale of, say, in the order of a kilometer. And these infragravity waves have to be well resolved by the model grid. You can apply a varying grid resolution, particularly in the cross-shore direction, based on the current condition. And we have lots of MATLAB scripts available in the MATLAB toolbox on OpenEarth and in Delft dashboard to do these kinds of things. But as a rule of thumb, you'll be having a varying grid size, with the largest grid size in the order of 50 meters offshore, and the smaller grid size in the order of about 2 meters at the beach and on your dune face. apart from grid resolution, you also have to think about the depth at which you're going to start the model, so the offshore water depth. The offshore boundary should be sufficiently deep that the infragravity waves are well described. And for this, you have to ensure that the group velocity to wave celerity ratio n is lower than about 0.8, 0.85 maybe. And you also want to ensure that there's no breaking of the short waves at the offshore boundary. These two graphs below here are sort of a visual guide to what depth you'd have to start your wave model, depending on the significant wave height that you're imposing in the left figure, and the wave period that you're imposing is given on the right figure. And the wave period here, we're describing the Tm minus 1, 0, where if you don't have a better measure, that's probably similar to the T peak over 1.1 roughly for a Johnson type spectrum. To have a good water depth at the offshore boundaries, you'd ideally be in the green areas, potentially in the yellow to orange, but know that you may be making errors already at the boundary by starting in such shallow water. At the boundaries, you should ensure that you have a uniform bathymetry, at least 3 cells, both on the offshore boundary as on the back boundary and the lateral boundaries. This is to ensure that the model is relatively stable in combination with the assumptions made at the boundaries for the Neumann conditions. Furthermore, if you're using cyclic boundary conditions, then obviously the bathymetry and the grid sizes on both lateral boundaries have to be identical, otherwise the cyclic condition is not met. Furthermore, in your XSpeech simulation folder, you must have a params.txt file, which is the file that defines all your model parameters. This file is a simple text file. Here's an example of part of a params.txt file, where keywords are defined, shown here in the green box, and the value shown in the blue box. The order in which you give keywords is not important to XSpeech. XSpeech will look for keywords that it recognizes, and it will look to see if there's an equals sign given at a keyword. If these conditions are met, then it will try and read the value to the right of the equals sign. Any other text that you add to the params.txt file will most likely be ignored by XSpeech, so you can add your own comments to here. There are some small exceptions which you are also described in the XSpeech manual. When getting started with XSpeech, we really recommend that you use the default model parameters as much as possible, especially if you don't know what the model parameters do in the model. The best way to ensure that you're using the default values is to not define a model parameter in the params.txt file. So if XSpeech can't find the definition of a certain model parameter in the params.txt file, it will automatically choose the best default value for that parameter. Moving ahead, if you're running a model and you have data to calibrate with, then it's really best to calibrate on waves and flow first, the drivers, as it were, of the morphodynamics at the beach, and then only after they've been calibrated to adjust sediment transport and morphology parameters to achieve the measured bed level response. There are a couple of useful parameters for these different parts of the XSpeech model. For instance, for waves, the break parameter will define what breaker model is used, whether it's the Rulfink breaker model or the Rulfink and Daly model for instationary runs, or the Baldock or Baches-Janssen breaker models for stationary runs, and the gamma value, which helps to define the intensity of braking. For flow, there's the bed friction, so the bed friction type that you want to use, the type of bed friction model, but also things such as vegetation fields that may affect flow. And then the flow boundary conditions, particularly at the lateral boundary conditions, can often be changed a bit to make sure that you have a stable model running over long periods of time. If you get into conditions of overwash and inundation, so things like barrier islands being inundated, then what we've seen in a lot of studies is that increasing the roughness on the barrier, particularly on vegetated barriers, improves the model results and the model physics being simulated. Two important calibration parameters in the sediment transport and morphology components of XSpeech are parameters relating to the asymmetry and skewness of the short waves. So in a parameterized way, the skewness and asymmetry of the short waves can be used to advect sediment in the direction of the wave propagation using the FAC-SK and FAC-AS keywords. So these keywords, they affect the direction and magnitude of sediment transport, particularly in the cross-shore direction. XSpeech is quite a computationally demanding model, and so as you get larger and larger model domains, you may be running into fairly extensive computation times. There's a number of ways to try and reduce the computation time. One way, without thinking about changing your model setup at all, is to run XSpeech on multiple cores and nodes using the MPI-enabled XSpeech executable, which is also available for download from the XSpeech website. But actually, a more systematic way to increasing the speed of the calculation is to think about optimizing your grid. So thinking about optimizing the number of grid cells that you're using and their grid size, both in X direction and Y direction, as in the number of wave bins that you're using. So, the theta min, theta max, theta discussed earlier. And the resolution that you need for this obviously varies per simulation and what you're trying to solve. But in 1D cases, for instance, you could think about using the keyword Snell's is one, which will set on Snell's law to compute the wave direction rather than the more costly standard wave directions solved by XSpeech. And you can also use the single DIR option, which is also described in the XSpeech manual, that may significantly increase your model speed as well as improve the predictions of infragravity wave heights. Obviously, if you're computing physical processes that you don't need, then you can turn them off. So for instance, if you're not actually interested in sediment transport and morphology, you can switch both those processes off in the params.txt file by setting morphology as 0 and sedtrans is 0, and that will save quite an amount of computation time. If you are interested in morphodynamic effects and less interested in the hydrodynamics and sediment transport, then you can think about using the morphological acceleration factor. But again, of course, take into account that you cannot increase the morphological acceleration factor to a great extent without expecting changes to occur or unrealistic changes to occur in the XSpeech model. And then finally, using more than one sediment type in the multifraction model will increase the computation time a lot. So consider using only one, which is the default for XSpeech. Okay, and then finally, if you run into trouble, the first thing to do is to look at the XSpeech log and warning files. These typically describe what's happening in the XSpeech model and why it stopped running. Examine the output results that you've received from XSpeech to see if there's any strange velocities or water levels occurring, bed level changes occurring. Particularly look around the model boundaries. Errors often occur on the boundaries of the model. In particular, the lateral boundary conditions can be quite problematic, particularly if you have a very complex coastline. To really bring a 2DH model back to basics, you could set the left and right boundary conditions to wall boundary conditions. It will stop all flow going through the lateral boundaries, or the no advec conditions, or even cyclic boundary conditions. And the same for the back shore. If you set that to a wall, that will not allow any flow to go out the back, but also maintain stability at the back for the XSpeech model. Also, instabilities in the model can be caused by having a morphological acceleration factor, a MOR factor that is too high, which leads to unrealistic bed level change within a time step, and then makes the model explode. And finally, if you run through all of these and can't find the root of the problem, or you've run into different troubles, then there's a forum on the XSpeech website, www.xspeech.org, where you can always post your question. So good luck modeling.